Scientists have figured out just how old our water is, and it's very old. It's so very old. The origins of Earth's water has been an enduring mystery. There are different hypotheses and theories explaining how the water got here, and lots of evidence supporting them. But water is ubiquitous in protoplanetary disks, and water's origin may not be so mysterious after all. A research article in Geoscience World Elements shows that other young solar systems have abundant water. In solar systems like ours, water is along for the ride as the young star grows and planets form. The evidence is in Earth's heavy water content, and it shows that our planet, the planet's water, is 4.5 billion years old. The article is "We Drink Good 5.5 billion year old water," and the authors are Cecilia Ceccarelli and Fujun Du. Ceccarelli is an Italian astronomer at the Institute for Planetary Sciences and Astrophysics in Grenoble, France, and Du is an astronomer at the Purple Mountain Observatory in Nanjing, China. The formation of a solar system starts with a giant molecular cloud. The cloud is mostly hydrogen, water's main component. Next are helium, oxygen, and carbon in order of abundance. The cloud also contains tiny grains of silicate dust and carbonaceous dust. The research article takes us through the history of water in our solar system, and this is where it all starts. Out here in the cold reaches of the molecular cloud, when oxygen encounters a dust grain, it freezes and adheres to the surface. But water is not water until hydrogen and oxygen combine, and the lighter hydrogen molecules in the cloud hop around in the frozen dust grains until they encounter oxygen. When that happens, they react and form ice water, two types of water, regular water and heavy water containing deuterium. Deuterium is an isotope of hydrogen called heavy hydrogen, HDO. It has a proton and one neutron in its nucleus. That separates it from regular hydrogen called protium. Protium has a proton but no neutron. Both these hydrogen isotopes are stable and persist to this day, and both can combine with oxygen to form water. When water ice forms a mantle on dust grains, the authors call it the cold phase, step one in the process they outline in their article. Gravity begins to exert itself in the cloud as matter clumps in the center. More mass falls into the center of the molecular cloud, and starts forming a protostar. Some of the gravity is converted into heat, and within a few astronomical units, AU, of the cloud center, the gas and dust in the disk reach 100 Kelvin degree, that's minus 280 Fahrenheit. 100 Kelvin is bitterly cold in Earth terms, only minus 173 degrees Celsius, but in chemical terms it's enough to trigger sublimation, and the ice changes phase into water vapor. The sublimation occurs in a hot Corino region, a warm envelope surrounding the cloud center. Though they also contain complex organic molecules, water becomes the most abundant molecule in Corinos. Water is abundant at this point, although it's all vapor. A typical hot Corino contains about 10,000 times the water in the Earth's oceans, the authors write. That's step two in the process outlined by the authors, and they call it the protostar phase. Next, the star begins to rotate, and the surrounding gas and dust form a flattened rotational disk called a protoplanetary disk. Everything that will eventually become the solar system's planets and other features is inside that disk. The young protostar is still gathering mass, and its life of fusion on the main sequence is still well in its future. The young star generates some heat from shocks on its surface, but not much, so the disk is cold, and the regions furthest away from the youngest protostar are the coldest. And what happens next is crucial, according to the authors. The water ice that formed in step one is released into gas in step two, but recondenses again in the coldest regions of the protoplanetary disk. The same population of dust grains is again covered in an icy mantle. But now the water molecules in that icy mantle contain the history of the water in the solar system. Thus, dust grains are the guardians of water inheritance, the authors write. That's step 3 in the process. In step 4, the solar system begins to take shape and resemble a more fully formed system. All the things we are accustomed to, like planets, asteroids, and comets, start forming and taking up their orbits. And what they do they originate from? Those tiny dust grains and their twice frozen water molecules. This is the situation we find ourselves in today. While astronomers can't travel back in time, they're getting better at observing the young solar systems and finding clues to the entire process. Earth's water contains a critical hint to the ratio of heavy water to regular water. Some detail is left out of the simple explanation given so far. When water ice forms in step 1, the temperature is extremely low. That triggers an unusual phenomenon called superdeterioration. Superdeterioration introduces more deuterium into the water ice than at other temperatures. Deuterium was only formed in the seconds following the Big Bang. Not much of it formed, only a deuterium for every 100,000 protium atoms. That means that if the deuterium was evenly mixed with the solar system's water, the abundance of heavy water would be expressed as 10 to 5, but there's more complexity to come. In a hot corino, the abundance changes. However, in hot corinos, the H2O to H2O ratio is only a bit less than 1 to 100. The authors explain H2O is water molecules containing 2 deuterium isotopes, and H2O is regular water containing 2 protium isotopes. There's even more extremity. To make things even more extreme, the authors explain the doubly deuterated water D2O is 1 to 1,000 with respect to H2O, namely about 107 times larger than what would be estimated from the D to H elemental abundance ratio. The ratios contain such large abundances of deuterium because of superdeuteration. At the moment that ice forms on the surfaces of the dust grains, there's an enhanced number of D atoms compared to H atoms landing on the grain surfaces. The in-depth chemical explanation is beyond the scope of the article, but the conclusion is clear. There are no other ways to obtain this large amount of heavy water in hot corinos nor in general, the authors write. Therefore, abundant heavy water is a hallmark of water synthesis in the cold molecular cloud clump during step 1 era. The important thing so far is that there are 2 episodes of water synthesis. The first happens when the solar system has not formed yet and is only a cold cloud. The second is when planets form. The 2 happen in different conditions, and those conditions leave their isotopic imprint on the water. Water from the first synthesis is 4.5 billion years old, and the question becomes, how much of that ancient water reached our Earth? To find out that, the authors observed the 2 things they could: the amount of water overall, the amount of deteriorated water, and the authors put it, namely a ratio of heavy water to normal water, HDO to H2O. More than enough water was created to account for Earth's water. Remember that the amount of water in the hot corino was 10,000 times more than Earth's water, and its HDO to H2O ratio is different from the water found in the initial cloud. How much of the corino water reached Earth? A hint can be found in the comparing HDO to H2O values in terrestrial water with those of hot corinos. Hot corinos are the only place we'd observe HDO in any still-forming solar-type planetary system. In previous research, scientists compared those ratios with ratios in objects in our solar system, comets, meteorites, and Saturn's icy moon, Enceladus. So they know that Earth's heavy water abundance HDO-H2O ratio is about 10 times greater than in the universe, and at the beginning of the solar system. Heavy over normal water on Earth is about 10 times larger than the elemental D to H ratio in the universe, and consequently at the birth of the solar system in what's called the solar nebula. The results of all this work shown that between 1 and 50% of Earth's water came from the initial phase of the solar system's birth. That's a wide range, but it's still a significant piece of knowledge. And the authors conclude, the water in comets and asteroids from which the vast majority of meteorites originate was also inherited since the beginning in large quantities. Earth likely inherited its original water predominantly from planetesimals, which are supposed to be the precursors of the asteroids and planets that formed the Earth, rather than from the comets that rained on it. Delivery by comets is another hypothesis for Earth's water. In that hypothesis, frozen water from beyond the frost line reaches Earth when comets are distributed and sent from the frozen Oort cloud into the inner solar system, and the idea makes sense. But the study shows that may not be true. It still leaves unanswered questions, though. It does not explain how all the water reached Earth, but the study shows that the amount of heavy water on Earth is at least the beginning of figuring this out. And in conclusion, the amount of heavy water on Earth is our Ariadne thread, which can help us to come out from the labyrinth of all possible routes that the solar system may have taken. Earth's water, 4.5 billion years old, just like the article says. At least some of it is. According to the authors, planetesimals probably delivered it to Earth, but actually exactly how it happens is not clear. There's a lot more complexity that scientists need to sort out before they can figure it out. The issue is quite involved because the origin of evolution of Earth's water is inevitably connected with other important particles on this planet, participants on the planet like carbon, molecular oxygen, and the magnetic field. These things are all wrapped up together in how life originated and how worlds formed. Water likely played a role in forming the planetesimals that deliver it to Earth, and water likely played a role in sequestering other chemicals, including the building blocks of life, onto rocky bodies that delivered them to Earth. Water lies at the center of it all, and by showing that some of it dates back to the very beginning of the solar system, the authors have provided the starting point for figuring the rest of it out. And here we presented a simplified early history of the Earth's water according to the most recent observations and theories. A good fraction of the terrestrial water likely formed at the beginning of the solar system's birth, when it was a cold cloud of gas and dust, frozen and conserved during the various steps that lead to the formation of planets, asteroids, and comets, and was eventually transmitted to the nascent Earth. How the final passage happened is another fascinating chapter, they said. And this is on Collective Spark by Even Go Universe Today. Please leave your comments, and thank you for your support. Kindly support my Patreon account. The daily posts are 5 videos daily, and they are totally different from what I have on my YouTube channel. Thank you so much for your support and that you find all my content so interesting. You'll find the Patreon account details in the description box.